Dear students, the next topic is analysis of trusses. Introduction to trusses. A truss is a structural member made up of number of bars, which is welded, bolted, or riveted at the joints, which is used to take up the load. Every truss element is in either tension or compression. Examples. The first example we can take it as a roof trusses. The second example, the bridge supports. The third example, crane booms. The fourth example, we can take it as antenna towers. The next example, it is power transmission towers. The last one, we can take it as a scaffolding. So these are the few examples of trusses. So we can see every truss, it is made up of number of bars. So number of bars which are joined together. So which is joined by means of bolted or by means of welded or by means of riveted. The main function of this truss, it is used to take up the load. Trusses are classified into two types. The first one is plain truss. The second one is face truss. Our syllabus, it is restricted only to the plain truss. So we have to carry out the analysis of the trusses only for 2D truss, that is a plain truss. What do you mean by plain truss? A plain truss is one where the plane of the structure remains in plane even after the application of loads. So the plain truss is one, it has to satisfy the equation. So that is M, which is equals to 2j minus 3, where M is nothing but number of bars and J is nothing but number of joints. The trusses, it is further classified as determinate and indeterminate trusses. A determinate truss is one which can be completely analyzed by using static condensation of equilibrium. That is summation of forces which is equals to 0 and summation of moments which is equals to 0. So the determinate trusses are those which can be completely analyzed by using the equilibrium equation. That is summation of forces and summation of moments, it must be equals to 0. Indeterminate trusses are the one which cannot be completely analyzed by using static condensation of equilibrium. So these are the trusses which cannot be analyzed by using the equilibrium equations. So such type of trusses we call it as indeterminate trusses. So in such cases, conventional methods becomes cumbersome. So figure below shows a 2D truss structure. This is the 2D truss structure. So each node, it has 2 degrees of freedom. So you can observe over here. So it is one bar element. This is one bar element. This is one bar element. So the bar elements, it is modeled together. So this we will treat it as a truss element. So every element. So when you take, this is the truss element. So it consisting of a node. Each node, it will have 2 degrees of freedom. That is, it will have a x displacement as well as y displacement. So each node, it possesses 2 degrees of freedom. The only difference between the bar element and truss element is that in the bars, both local and global coordinates are same, whereas in trusses, these are different. That is the main difference between the bar element and the truss element. So in order to do analysis of trusses, some assumptions are to be made in the trusses. The first assumption is a load on a truss can only be applied at the nodes or the joints. That is the first assumption. That means, so you have to apply the loads only at the nodal points. So load, it cannot be applied on the truss element. Second assumption, due to the application of the load, each bar of a truss is either induced with tensile or compressive forces or stresses. So as soon as the load is applied, So each bar or each truss element, it has to undergo either tension forces or it has to undergo compression forces. The third assumption, the joints in a truss are assembled to be frictionless pin joints. Since the number of bar elements it is assembled together, or we will call it as a truss. So the truss element it is assembled, it is joined at the points. So these points, so it should be always frictionless pin joints. That is the third assumption. The next assumption is the self weight of the bars of a truss are neglected in comparison to external load applied. That is, the self weight of the bars, it is negligible or it is neglected when we compare with the externally applied load. The next assumption, truss element is only a prismatic member. So the prismatic member is the one, so where the cross section area is uniform along its length. The next assumption is load is independent of time. That is a constant load which is going to be act on the trusses. The next topic will go for derivation of transformation matrix for a 2D truss element. So let us consider a truss element as shown in figure having two nodes 1 and 2. So this is the truss element. It consisting of two nodes, node 1 and node 2. The coordinate system that passes along the element, it is represented by x dash axis, is called as local coordinate. So this is the truss element. So along the axis, so along the element, so the axis is represented, that is x dash. This coordinate system, we call it as the local coordinate system. And the coordinate xy system, we call it as global coordinate system. So we have one more coordinate system, that is xy. So this xy coordinate system, we call it as the global coordinate system. So here the truss element, it is represented in local coordinate system as well as the global coordinate system, that is x dash as well as xy. After the application of load, let us assume that the element takes a new position. So as soon as the load is applied, it will take a new position, so that the node 1, it has displaced by an amount of q1 dash. So here node 1 is there. As soon as you apply the load, so the node 1, it will displace us to somewhere at this particular point. The node 2, it will displace us somewhere over here. So when we take in local coordinate system, so along this, so the node 1, it will displace us for an amount of this much distance. So that distance, I'll represent it as a q1 dash. So in local coordinate system, node 1, it has displaced by an amount of q1 dash. Similarly, the node 2, it will displace us an amount of q2 dash. It is moved by an amount of q2 dash. So the q1 dash and q2 dash are the nodal displacements of the truss element 1 and 2 in local coordinate system. Similarly, when we take a global coordinate system, so each node, it possesses 2 degrees of freedom. So now let us assume that at node 1, the displacement along x direction, I will call it as a q1. The displacement along y direction, I will call it as a q2. So q1 and q2 are the nodal displacements along x and y direction at node 1. Similarly, when you take a node 2, at node 2, the x displacement is q3, the y displacement is q4. So this is what the truss element which has been taken in order to derive the transformation matrix. So which is represented both in the local coordinate system as well as the global coordinate system. Now from the figure, so from this point I will simply draw one line. So the distance from here to here I will represent it as a. The distance from here to here I will represent it as a. Now let us assume that the truss element, it is inclined at an angle of theta with respect to the global coordinate system. From the figure, we can see cos theta, which can be written as A by Q. So you take a triangle of this. So this is the theta. So this is the opposite, adjacent, hypotenuse. When you take a cos theta, we'll get A by Q1. A by Q1. Similarly, so you extend the line over here. The included angle, it will be theta. So this is the opposite, adjacent, hypotenuse. So you just go for sine theta. When you go for sine theta, so this is the opposite. The opposite is B. The hypotenuse is Q2. So it is B by Q2. Now I will rearrange this. So A is equals to Q1 cos theta and B, which is equals to Q2 sine theta. Again from figure, the Q1 dash. Q1 dash, it can be written as it is the sum of A plus B. So Q1 dash, which is equals to A plus B. So if we know the value of A is Q1 cos theta, the value of B is Q2 sin theta. You just substitute to this. So we'll get Q1 dash, which is equals to Q1 cos theta plus Q2 sin theta. You call it as equation number 1. Similarly, we get the Q2 dash. So the Q2 dash, it is also again you draw one line over here. So this it will form one triangle. Again here it will form one more triangle. So similarly the Q2 dash, it can be written as Q3 cos theta plus Q4 sin theta. Call it as equation number 2. Now writing the equations 1 and 2 in matrix form. So left hand side we have Q1 dash, Q2 dash. So here Q1, Q2, here Q3, Q4. So I will remove Q1, Q2, Q3, Q4. In the equation, when you remove Q1, Q2, so we'll get the cos theta, sin theta. We don't have Q3, Q4, we'll get 0, 0. So cos theta, sin theta, 0, 0. Cos theta, sin theta, 0, 0. Similarly, in second equation, so Q1 and Q2 are absent, so 0, 0. So Q3 is cos theta, Q4 is sin theta. In the brackets, you write Q1, Q2, Q3, Q4. So now let us assume that cos theta, I will call it as a L. Sin theta, I will call it as a M. Where L and M are direction cosines. So substituting the L and M to this matrix, we will get Q1 dash, Q2 dash, which is equals to LM 0, 0, 0, 0, LM into Q1, Q2, Q3, Q4. So therefore, this matrix Q1 dash, Q2 dash, I will write it as a Q dash. So it is the nodal displacement in local coordinate system. And this matrix LM 0, 0, 0, 0, LM, I will represent it as a capital L. And Q1, Q2, Q3, Q4 are the nodal displacements in global coordinate system. I will represent it as a Q. So where Q dash, which is nothing but nodal displacement in local coordinates, L is nothing but transformation matrix, Q is nothing but nodal displacement in global coordinates. So this is the derivation of transformation matrix for a truss element, which is represented by L. So where L is the transformation matrix, which is given as LM0000LM. Now, so before going further, so we need to know the direction cosines. So cos theta and sin theta are the direction cosines. So for a truss element, we have to find out the value of direction cosines. So for that, simply I have taken one truss element having nodes 1 and 2. It is represented in Cartesian coordinate system. Let the node 1 is located at a distance of x1, y1. The node 2 it is located at a distance of x2, y2. Let the length of the element, I'll take it as a LE. The truss, it is inclined at an angle of theta with respect to the global coordinate system. So when you take a horizontal distance of this, the horizontal distance will get it as x2 minus x1, and vertical distance it will be y2 minus y1. Now we can find out, go for cos theta. So cos theta is nothing but adjacent by hypotenuse. So adjacent is x2 minus x1 divided by L. Similarly, sin theta is nothing but y2 minus y1, that is opposite by hypotenuse. So y2 minus y1 by L. So that is what the value of L and M. for a truss element. Similarly, we can find out the length of the element. So you apply the Pythagoras theorem. So hypotenuse square, which is equals to adjacent square plus opposing square. So LE square, which is equals to x2 minus x1 whole square plus y2 minus y1 whole square. So you apply the square root. So that gives the length of the element. So these three equations, so we frequently use it. We will use so to solve the problem. The next topic is the derivation of stiffness matrix for a truss element. So a truss element is equivalent to a 1D bar element in local coordinate system. Hence, the strain energy for truss element in local coordinate system, which is given by strain energy, which is equals to U, which is equals to half times of Q transpose K dash Q dash. So K dash is the stiffness matrix of a truss, which is treated as a bar element, and Q dash is nothing but the nodal displacements in local coordinate system, and Q, which is nothing but the global displacement vector, which is represented in global coordinate. So where the value of K dash, which is nothing but AE by LE 1 minus 1 minus 1 1. So this is the value of the stiffness for a bar element. Also the Q dash. So Q dash, which is nothing but L into Q. Just now we derived this. So derivation of transformation matrix. So from that we'll get Q dash is nothing but L into Q. Similarly, Q is also which is nothing but L into Q only. So substituting this to the return, so strain energy which is equals to half times of Q is L into Q transpose K dash. So Q dash I will write as a L into Q. I will apply the transpose. So half times of Q transpose L transpose K dash L into Q. I will rearrange this. So half times of Q transpose L transpose K dash L into Q. So this term I will represent it as a Ke. So which is equals to half times of Q transpose K into Q, where Ke is the stiffness matrix of truss element. Now we have to find out the value of this, right? So Ke, which is equals to L transpose K dash into L. So we know that from previous derivation, so the transformation matrix L. So L, which is given as Lm 0 0 0 0 Lm, and hence you take a transpose of this L transpose, which is equals to L0 M0 0 L 0 M, and K dash, which is nothing but the stiffness matrix of the bar element. Now you substitute everything to this equation. So when you substitute this, so we get so L transpose L0 M0 0 L 0 M into AE by L 1 minus 1 minus 1 1 into LM 0 0 0 0 L. So AE by L, it is a common, you just keep it outside. You multiply this matrix with this matrix. So when you multiply this, so 1 into L, it becomes L, 0 into minus 1, it becomes 0. So you'll get a L. Again, L into minus 1 minus L plus 0 into 1, it becomes 0. So you'll get minus L. Similarly, take a second row. So M into 1, it is M plus 0 into minus 1, 0. So we'll get a M. Again, M into minus 1 minus M plus 0 into 1, it is 0. So we'll get minus M. Similarly, you take this. So 0 into 1, 0 plus L into minus 1 minus M. So 0 into minus 1, 0. So 1 into L, we'll get L. So 0 into 0 into 1, it is 0 plus M into minus 1 minus M. So 0 into minus 1, 0. So M into 1 will get M into, you write this matrix. Again, you multiply these two matrix. So row into column. So L into L square plus minus 1 into 0, 0. So L square plus 0, it is L square. Again, you take this with respect to the second one. So L into M, Lm plus minus L into 0, 0. So we'll get Lm. So third one, so L into 0, 0 plus minus L into L square. So we'll get minus L square. So L into 0, 0 plus minus L into M minus L, minus L. Similarly, you expand the second row into the same procedure. So we'll get this matrix. So that is a KE, which is equals to AE by LE in the bracket L square LM minus L square minus LM. LM M square minus LM minus M square minus L square minus LM L square LM minus LM minus M square LM M square. So this is what the stiffness matrix for a truss element in global coordinate system. The next topic is derivation of stress matrix for a truss element. So the stress matrix for a truss element in local coordinate is equivalent to a 1D bar element. So we know that stress, which is defined as stress which is equals to EBQ, but the Q will represent in the local coordinate system. So that is Q dash. We know that, so the value of B, that is strain displacement matrix, it is treated as a 1D bar element, which is given as 1 by LE minus 1, 1, and Q dash, which is nothing but L into Q. So therefore, stress, which is equals to EB LQ. Now you substitute for this. So E into B, B is 1 by LE minus 1, 1. L is the transformation matrix LM 0, 0, 0, 0, LM into Q. When you take a single element, so it consisting of 4 nodal displacements Q1, Q2, Q3, Q4. You multiply these two matrices. So E by LE will get, so when you multiply this, minus 1 into L minus L plus 0. So minus L comma minus 1 into M minus M plus 0. So minus M minus 1 into 0. So 1 into L will get L. So minus 1 into 0, 0. So 1 into M. So we'll get M. So minus L minus M L M. So this is what we call it as a B matrix for the truss member. So E into 1 by LE minus L minus M L M into Q1, Q2, Q3, Q4 is the stress matrix for a truss element. The next one, we can find out the reactions for the truss element. It is similar to the bar element. The reactions of the supports for a truss element, it is found by using R, which is equals to K into Q minus F. So that is the equilibrium equation. We have to expand the corresponding the rows and columns in the equilibrium equation. We'll get the reactions. So in order to solve this problem, so all the above matrices you should remember. That is a stiffness matrix, stress matrix, transformation matrix, and the reaction. Now let us start with a simple numerical on trusses. For a truss element shown in figure 1, determine the nodal displacement, the stresses in each element, reactions at the support. Take area of truss element as 200 mm square and Young's modulus as 2 into 10 to the power of 5 Newton per mm square. So this is the truss element. So the load is applied exactly at this particular point. So it consisting of two trusses. This is one truss, this is one truss with the two supports and the dimensions here given. So go to the solution. So the first step, so as usual, so that is you have to represent the finite element model. So take the model. So the first thing is, so you have to represent the element numbers. So in the problem, element numbers are not defined. If it is defined, you take as it is. If it is not defined, you have to define the element numbers. So in the problem, I am defining this as element 1 and this as element 2. So once you define the element numbers, the next step is you have to locate the node numbers. So here we have a fixed support. So you have to locate one node. Here the load is applying. So you have to locate one node. And here you have a support. You have to locate one node. So you can model this, the truss structure, by taking three nodes. So node 1, node 2, node 3. So this numbering of the nodes, it should be always in sequence. Also, let us assume that at node 1, the displacement along x direction, I will take it as a q1. Along y direction, I will take it as a q2. Come to node 2, the displacement along x direction, I will take it as a q3. The displacement along y direction, I will take it as a q4. Similarly, at node 3, along x direction it is q5, along y direction it is q6. So this is the first step. So you have to locate element numbers, locate the nodes, and you locate the nodal displacements. Go to the next step. So the next step, so you have to represent the nodal data. So you have to draw one table. So node number x, y. So in the given problem, how many nodes are there? 1, 2, 3. You write down here node 1, node 2, node 3. X and y are, so that is the dimensions are the coordinate points of the nodal numbers. So in order to define the value of x and y for node 1, in the problem you have to choose the origin. So choosing of the origin is very important. You can choose anywhere. You can choose the origin over here. You can choose the origin here. You can choose the origin over here. But in the problem, I have chosen the origin is exactly at this particular point, because in order to get all positive values, so I have chosen the origin for this problem is over here. If I choose the origin is over here, the distance of node 1 from the origin, it will be 500 plus 400. That is what the value of x. So here you enter the value of x coordinate, that is 900. The value of y is 0. Go to the node 2. From the origin, the node 2, it is located distance of 500 mm in x direction, and in y direction it is located distance of 300. So the coordinates for node 2, it will be 500 comma 300. So 500 300. Similarly for node 3, the origin is over here, so the value of x is 0, the value of y is 300. So 0 300. This is what the nodal data. So as soon as you look at the node numbers, the next step is you have to represent the nodal data. So after representing nodal data, you have to draw element connectivity table. So the element connectivity table, it consisting of element number, initial node, final node, length of the element, L and M, direction, coordinates. In the problem, we have only two elements. So I will represent element 1, element 2. So after representing element number, you have to choose the initial node and final node. So when you take element 1, it consisting of two nodes, that is node 1 and node 2. Among these two, you have to choose which one is the initial node and which one is final node. So in the problem, I will take the node 1 as the initial node and node 2 as the final node. So 1, 2. Similarly for second element, so I'll take 2 is the initial node and the 3 is the final node. 2, 3. So node numbers. You can take random. It is left to you. So better. So choosing of the initial node and final node, you just follow in always sequence. Now you have to find out the length of the element. So for element 1, you have to find out the length of the element. So in order to find out this, I have shown. So we have one equation LE, which is equals to square root of. So there I have represented two nodes, that is x2 minus x1 whole square plus y2 minus y1 whole square. So here we have one more that the same equation is reformulated like this. So length of the element, which is equals to x of final minus x of initial square plus y of final minus y of initial square. So here, so x of final, here the initial node for element 1 it is 1, the final node for element 1 is 2. So x of final means it becomes x2 minus x1 whole square plus y2 minus y1 whole square. Now you know value of x2. X2 you can come over here. This is the value of x2. So 2. So x2 is 500. X1 is 900. So 500 minus 900 whole square plus. So y2 minus y1. So it is 300 minus 0 whole square. From this we'll get length of the element as 500 m. Similarly, we have to find out the length of the element for the second element. Since it is a horizontal, the length of the element for second element, it is directly we can write it as a 500 mm. If it is horizontal, if it is vertical, directly we will get the length of the element. If it is inclined, use this formula. So after this, you have to find out the direction cosines L and M. So L. So L is nothing but cos theta, M is nothing but sin theta. So you forgot about that. So here also we have one equation. So L, which is nothing but x of final minus x of initial divided by length of the element. If you want to find out the value of L for first element, so go for the final node and initial node. Which is the final node and which is the initial node for element 1? For element 1, the final node is 2, the initial node is 1. So this equation, it remodifies as x2 minus x1 divided by length of the element. So you know value of x2. x2 is 500. The value of x1 is 900 divided by length of the element is 500. Substitute over here, you will get the value of L as minus 0.8. Similarly, we have to find out M. So for M, it is y of final minus y of initial divided by 2. For element 2, the final node is 2, the initial node is 1. So this we can write it as y2 minus y1 divided by length of the element. So y2 is how much? 300 minus y1 is 0. So 300 minus 0 divided by length of the element is 500, which is equals to 0.6 mm. You just substitute this minus 0.8 and 0.6. Similarly, you find out the value of L and M for the second element. In order to find the L, so L is which is equals to x of final minus x of initial divided by LE. So come over here, the final node is 3, the initial node is 2. So the value of L becomes what? X3 minus x2 divided by LE. So value of x3 is how much? 0 minus x2. It is 500 divided by length of the element is 500. So 500 divided by 500, you will get minus 1. Similarly, go for M. So y of final minus y of initial divided by length of the element. So final node is 3, initial node is 2. So y3 minus y2 divided by length of the element. So y3 is how much? 300 minus y2. It is 300. So it is 0. 0 by anything, it becomes 0. So this is the way of finding the L and M or direction cosines L and M. So the next step is you have to find out the elemental stiffness matrix for a truss element. So which is given as K is nothing but AE by L, this matrix, L square, Lm minus L square minus Lm. Lm are direction cosines. So go for element 1. So for element 1, K1 which is equals to A1, E1, L1, you write down the matrix which is equals to, area is same in the problem. So it is 200 mm square. So 200 mm square. E is 2 into 10 to the power of 5 divided by length of the element. So for element 1, length is 500 into the bracket. You know value of L and M. So L is minus 0.8, M is 0.6. So you square this L square. So minus 0.8 square. So that is 0.64. Again L into M, 0.8 into 0.6 will get minus 0.48. Similarly minus L square. So we'll get minus 0.64 minus Lm will get 0.48. So the same thing. So the first two terms will be repeated with the opposite sign. So as soon as you complete this, write the row as a column. Again go for m square. So m square, so it is 0.6 square, so it is 0.36. See, once you write these two, write the same thing over here with opposite sign. Now the same thing you write over here. So you will get the two values right over here with opposite sign. Again these two values right here with opposite sign. So that's complete the value of k1. Now you simplify this. When you simplify this, we'll get 8 into 10 to the power of 4. Now you have an option. You can keep 10 to the power of 4 outside and you can send 8 inside. When you send 8 inside, so it becomes too complicated. Since in the given problem, area it remains same, Young's modulus it remains same, and you can observe the length of the element also it remains same. So the product of this in element 1 and element 2 it remains same. So you keep as it is, don't send inside. So if you send inside, it becomes too complicated. So better you keep it outside. So this choice you have to think it. So if area is different, length is different, so it's compulsory you have to send the term inside into the matrix. So I'll keep as it is, bracket. So write as it is the terms. Now for element 1, so we have taken two nodes. We have represented the nodal displacements as 1, 2 at node 1, 3, 4 at node 2. Now in the matrix, so you have to write down the values of this 1, 2, 3, 4. This, it again it depends upon, so the initial node and final node. Be careful about this. See, for element 1, I have taken the initial node as 1, the final node as 2. So initial node it consisting of the nodal displacements 1, 2. The final it consisting of 3, 4. So the sequence it will be 1, 2, 3, 4. So here we have to write in the same sequence 1, 2, 3, 4. Again here 1, 2, 3, 4. Suppose in the problem, if you taken the 2 as an initial node, 1 as a final node, then you have to represent it as 3, 4, 1, 2. So here you have to represent 3, 4, 1, 2, 3, 4, 1, 2, like that. Now you go for element 2. So K2 which is equals to A2, E2, L2 in the bracket. So write down the stiffness matrix. So which is equals to 200 into 2 into 10 to the power of 5 divided by length of the element is 500 into L square. So for second element, L is minus 1, M is 0. So 1 square is 1, L into M 0. So write the same two terms with opposite sign. So write this over here, M square is 0. Write again these two values over here with opposite sign. Again these two values over here opposite sign. Again these two values with opposite sign. So you remove. So when you do the simplification, we'll get 8 into 10 to the power of 4. Don't send inside because already we removed 8 into 10 to the power of 4 in element 1. So you have to keep the same thing for element 2. So write the terms and you have to represent the node numbers. So go to the element 2. For element 2, the initial node is 2, the final node is 3. So 2 is the initial node, 3 is the final node. So we have to represent it as 3, 4, 5, 6. So 3, 4, 5, 6, 3, 4, 5, 6. So this is the way of finding the stiffness matrix for individual elements. So after this, we have to find out the global stiffness matrix, that is K, which is equals to sum of the individual stiffness matrices K1, K2. So therefore K, which is equals to, so in both the stiffness so matrices, we have 8 into 10 to the power of 4 is the common term. So 8 into 10 to the power of 4 in the bracket. So totally we have 6 nodal displacements. You write over here 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Now we have to write the elements in the global stiffness matrix. So you follow the same procedure as uh, I thought in bars. So this is the element of K11, K12, K13, K14, K15, K16. So it is K11. So it is 1 cross 1. So search for 1 cross 1. So 1 cross 1, it is 0.64. Here we don't have 1 cross 1. So you write it as a 0.64. Again, this is 2 cross 1. So search for 2 cross 1. So 2 cross 1, we have minus 0.48. 2 cross 1, here it is not there. So you write here it as a minus 0.48. The third one, so it is 3 cross 1. So go for the matrix. So 3 cross 1 minus 0.64. Here we don't have 3 cross 1. So minus 0.64. Again, go for 4 cross 1. 4 cross 1, it is 0.48. Here we don't have 4 cross 1. So you write it as a 0.48. Go for 5 cross 1. So when you go for 5 cross 1, here we don't have any 5 cross 1. Here also we don't have any 5 cross 1. So you enter it as a 0. Again, go for 6 cross 1. So when you go for 6 cross 1, here it is not there. Here also it is not there. You enter it as a 0. So we got the first row. So write the first row as a first column. Again, go for this term. So it is 2 cross 2. So 2 cross 2. So when you go for 2 cross 2, so we have 0.36 over here. Here we don't have any 2 cross 2. So you write it as a 0.36. So similarly, you find out the remaining terms. So 3 cross 2, 4 cross 2, 5 cross 2, 6 cross 2. Write the second row as a second column. Again, repeat this. Write it as a column. So this is a way of finding the global stiffness matrix. The next step is we have to determine the global force vector. So F, which is equals to, so since the truss element it is represented in 2D format, every node it will have the 2 degree of freedom. So the forces also it will act along x direction as well as y direction. So at node 1 the force is F1, F2. At node 2 the force is F3, F4. At node 3 the force is F5, F6 transpose. So load is applied at node 2 in y direction. So it is we have taken the coordinates which is along x and y axis. So load is acting in downward direction. So we have taken it as a negative value. So minus 12 into 10 to the power of 3. Similarly, determine the global displacement vector q, which is equals to q1, q2, q3, q4, q5, q6 transpose. After this, you write down the equilibrium equation, so which is represented as k into q, which is equals to f. So this is the global stiffness matrix multiplied by the displacement vector, which is equals to the global force vector. So after writing the equilibrium equation, you have to apply the boundary condition. So in the given problem, the boundary conditions are the node 1. So the node 1 as well as node 3, it is fixed. So the displacement at node 1, that is q1, q2, both x and y displacement, it is 0. Similarly at node 3, the x displacement is q5 and y displacement is q6, which is equals to 0. So this is what the known boundary conditions. So node 1 and node 3 are fixed. So the corresponding the displacements q1, q2, q5, q6, which is equals to 0. So imposing them by elimination method. So according to the elimination method, wherever the boundary conditions are known, the corresponding the rows and columns, it has to be eliminated. So eliminate first row, first column, first row, first column, eliminate second row, second column, and eliminate fifth row, fifth column, and sixth row, sixth column, fifth, sixth, fifth, and sixth. So after applying boundary conditions, so the equilibrium equation again it remodifies. So it will result 8 into 10 to the power of 4 1.64 minus 0.48 minus 0.48, 0.36 into Q3, Q4, which is equals to 0 minus 12 into 10 to the power of 3. Now you have to solve this matrix. So the next step, solve for nodal displacement, stresses and reactions. So solve this matrix, you expand it, so we'll get nodal displacements, that is Q3, Q4. So Q3 is minus 0.2 mm and Q4 is minus 0.683 mm. After finding nodal displacement, so you calculate the stresses in each element. So for element 1, the stress which is given as sigma 1, which is equals to E by L1 minus L minus M Lm into the element 1, it consisting of the nodal displacements Q1, Q2, Q3, Q4. Here also you have to take it in sequence. So we have taken the node 1 as initial node and node 2 as final node. So it is Q1, Q2, Q3, Q4. So substitute everything and you just multiply these two matrices, we'll get minus 100 Newton per mm square. Similarly for second element, sigma 2 is nothing but E by LE L2 minus L minus M Lm Q3, Q4, Q5, Q6. So E is 2 into 10 to the power of 5, length is 500. So L it is minus 1 and M is 0. So 1 0 minus 1 0 into Q3, Q4 0 0. So expand this, we'll get minus 80 Newton per mm square. And the last one is we have to find out the reactions. So reactions, it will result at two nodes, that is node 1 and node 3. At node 1, it will result two reactions. One it is along x direction and one it is along y direction. So R1 is the reaction along x direction, R2 is the reaction along y direction. Similarly, we have to find out the reaction at node 3. At node 3, so the reaction is R5 and R6. R5 it is along x direction, R6 it is along y direction. So in order to find out the reactions, just you have to expand the equilibrium equation, right? So R1, so expand the first row. So when you expand the first row, we'll get K11 Q1, K12 Q2, K13 Q3, K14 Q4, K15 Q5, K16 Q6 minus F1, which is equals to 0 or which is equals to, you just substitute the values of this, the terms. So we'll get the reaction at node 1 along x direction, which is minus 15.998 kilonewton. Similarly, we want the reaction at node 1 along y direction. It is represented as R2. So expand the second row of the equilibrium equation. We'll get the value of R2 as minus 11.990 kilonewton. Similarly, you expand the fifth row and sixth row, we'll get the corresponding the reactions.